Okay, I think we can get started. Good afternoon, everyone. My name is Brian Somm. I'm the department chair. It's my pleasure to welcome you to the third and final distinguished colloquium for the semester, and I'm going to turn it over to Professor Forbes in just a minute to introduce our speaker. But before I do that, one of the things that is one of my privileges as being chair of the department is to work with an absolutely fantastic staff. And earlier this year I was privileged to join Tom Johnson in a breakfast that celebrated his 25th anniversary as an employee of received that certificate. So, and as I said, we're all grateful for everything that Tom does in the department, from making sure that everybody's talk is set up, to handling demo shows, to just putting WD-40 where it needs to go. Thanks, Tom. Okay, and with that, I'll turn it over to Professor Forbes to introduce our speaker.
Thank you very much. It's my pleasure to welcome Bill Unruh to WSU to speak with us today. He graduated from Princeton, where he worked with John Wheeler. And then he said, now UBC, and he's at University of British Columbia in Vancouver. That's where I met him. I was a student there. And a Hagler Fellow at Texas A&M. And he's won numerous awards, including the Fellowship of the Royal Society of London, and has worked on many different topics in physics at the overlap of quantum mechanics and relativity and thermodynamics. Famously known for the Unruh effect, relating Hawking radiation, but in accelerating reference frames. And so he merges all these branches of physics. He basically knows physics extremely well. And when I was a student at UBC, if you ever had a question about physics, a deep question that you couldn't understand, you'd go talk to Bill, and he'd sit there, and you'd explain it to him, and then he'd think for a little bit, and then give you insight. And unlike a lot of other people who I've done this with, his insight almost always turned out to be correct. Anyway, you don't want to hear me speak? Bill, thank you very much for coming. Join me in welcoming Bill Unruh.
Thank you very much. It's been a pleasure being here. I think I can say I was pleasantly surprised what I discovered when I came here. So, yeah, thanks for inviting me. And what I would like to talk to you about today is, as you can see here, the generic title is Experimental Black Hole Evaporation. It's basically talking about the use of analogs in getting insights into physical systems, especially physical systems where you don't understand what's really going on. I think one of the most amazing aspects of modern physics is this role of analogy in the field, in particular the analogy between what's going on out in the world there and mathematics. That one can write down mathematical equations, which of course have absolutely nothing to do with the world, it would seem. And yet by using them, and often using exactly the same mathematics in totally different fields, get insight into why the world works as it does. In this particular case, what I want to do is to ask the question as to whether or not one can understand gravitational particle creation, in particular around a black hole, by the use of other systems. Certainly back when I got involved in the field in the 1970s, I didn't believe, gravity was special. Black holes were special. There was nothing like black holes, so there was nothing to that you could make them an analogy, use as an analogy for them. And I discovered that that was false. Of course, the argument from analogy is an ancient one. People all the way back to the Greeks have used it. And there's always the question as to how far the argument from analogy is a good one. because any time one has an analogy, it's good in some areas and it's not so good in other areas. If the two things were absolutely identical, then of course they would no longer be an analogy, they would just be the same thing. And part of what's interesting is that it's not only the parts where A is analogous to B, where they're similar to each other, that are important, but also the parts where A is not similar to B, because that tells you where your argument, what are the things that your argument depends on. So if A and B are not similar to each other, and yet they give exactly the same results, that tells you something. And we're going to find that out here. So the field that I want to look at is the one which in 1974, Stephen Hawking showed that black hole has a mass m, that black holes had a temperature. Now, a black hole is defined as a region of space-time into which things can go, but nothing can come back out. That surface is like a surface of light. It's traveling outwards as fast as it can, namely at the velocity of light. Of course, it's not getting anywhere. But that means that anything that would try to get out would have to be traveling faster than light. Can't do. So how in the world could this thing have a temperature? A solar mass black hole, which is a few kilometers in diameter, has a temperature of about 10 to the minus 5 Kelvin. Not very warm. Basically, the wavelength of the radiation is roughly the size of the black hole. And that defines the temperature. Small black holes are hotter. Big black holes are cooler. So when a black hole loses energy, its temperature goes up, not down. One usually thinks about things sitting there, a hot thing sitting there radiating, that it's going to get cooler. Here, as the thing radiates, it gets hotter, but smaller, because after all, the mass of the black hole is E equals mc squared, the energy of the black hole. One can apply the laws of thermodynamics, TdS equals dE. E is just m. We'll work in units in which C is equal to h bar is equal to Boltzmann's constant, and sometimes is equal to 2 pi is equal to 1. So, since the temperature is 1 over the mass, dE divided by T is dm divided by 1 over m, which is m dm. That tells us that the black hole has an entropy which is proportional to the mass squared. And in fact, twice m is the radius of the black hole. So this turns out to be just 1/4 of the surface area of the black hole. The smaller the black hole gets, the lower its entropy is. Now, I could give a whole lecture on this, and this is a topic that has now generated 40 years of controversy and is still controversial. What is this entropy? Is it an entropy in the old-fashioned thermodynamic sense, or is it an entropy in the statistical mechanics sense, namely as a measure of the sort of chaotic behavior of the microstates of the system, a counting of the microstates of the system? And people are still arguing about which of those is the right way to view it. But that's not the talk I want to give today. One of the problems with Hawking's derivation is that it makes no physical sense. It's certainly right mathematically. The mathematics he did was all good. But when you look in the details of what his calculation was, you say, wait a minute, this doesn't make any sense. In what sense do I mean that? Well, let's take a look. This is supposed to be a diagram representing a black hole. This green stuff is matter that falls in to form the black hole. This black is the horizon in a special coordinate system, but it doesn't matter. This is the horizon. It stays the same radius pretty well after the matter has fallen in. And if we follow light rays, for example, from the past, or rather from the future, if we separate these light rays by 1 over the frequency, and where the typical frequency is the typical frequency of the temperature for the black hole, and ask where did those light rays come from, or where did that radiation come from? Well, it came from the behavior of the quantum field in the past. It can't have come from inside the black hole because nothing can get out of the black hole. So if I go back into the past, I find that these light rays have to squeeze up closer and closer to the horizon. And in fact, they squeeze up exponentially close to that horizon, so that if we go into the past, the effective frequency here compared to the frequency here goes exponentially as the time at which we look at the frequency up here. It goes roughly as the time divided by the mass converted into temporal units. That's about 10 to the minus 5 seconds for the black hole. And so for a solar mass black hole, the initial frequency is about the final frequency times e to the 10 to the 5th times t. Now, even if I take t to be 1 second, e to the 10 to the 5th is a large number. It's an extremely large number. It's so big that I don't have to tell you what units I measure anything in. Because whether I measure the time in terms of Planck times 10 to the minus 44 seconds, or I measure it in terms of ages of the universe, 10 to the 10th years, that difference in units makes only a trivial difference in this 10 to the 5th. And notice that if I wait 2 seconds, it's no longer 10 to the 5th, but 2 times 10 to the 5th. And if I wait 10 seconds, it's 10 to the 6th, etc. Now, if I ask, if I've got a photon or something coming in here with that frequency, what's its mass? Well, its mass is e to the 10 to the 5th times the mass of the whole universe. So I'm now imagining a physical system where I've got some quantum fluctuation here whose mass is e to the 10 to the 5th times the mass of the whole universe, comes wandering in towards a black hole. Is the black hole just going to sit there and not notice it? Clearly, that would affect the black hole. So the basis under which I started to do this calculation, or under which Hawking started to do this calculation, just really doesn't make any sense. And if we try to get rid of this, then you find you get no Hawking radiation. Of course, if we could do an experiment, we'd know what the answer is. The trouble is that a solar mass black hole has a temperature of 10 to the minus 5 Kelvin. That's a little bit hard to see against the 3-degree microwave background radiation that's all over the place, especially if this object is very far away from us. And, you know, the intensity drops as 1 over r squared. And you're just not going to see them. And, you know, maybe one could make a small black hole in the lab, that would be much hotter. We could see that more easily. But it's really, really, really hard to make a small black hole in the lab. And besides, might be a little bit dangerous. So what can we do? Back when I was a postdoc with Roger Penrose, I was asked by Dennis Schauma to come to Oxford to give a colloquium on black holes. And I was desperately trying to think of how does one explain black holes to an audience of physicists. This was, remember, a time when black holes were not objects which you could go down the street of Pullman, ask any arbitrary kid on the street, and he would tell you what a black hole was. That wasn't true in those days. So, an analogy. Imagine that we live in a world, let's say Terry Pratchett's Discworld. How many of you have read Terry Pratchett? The rest of you should. Anyway, he postulates a world, a disk world, a flat world in which magic is the sort of dominant thing, and there's some kooks there that do this sort of materialist science, but they're not getting very far. Anyway, this disk world is a disk with a huge ocean. The ocean falls over the edge of the disk world. The disk world is incidentally carried on the back of a huge turtle, which swims through space. And the water pours over the edge. Terry Pratchett's been asked, why doesn't the water all disappear? And he says, it's arranged. You can do that if you're an author. And this has got some fish in it. And in particular, it has some physicist fish. The fish are the physicists. And this professor over here wants to do some experiments. And he sends his graduate student out near the edge of this great waterfall. Now, when the graduate student is sitting out here, he speaks to the professor. Notice I don't have the professor speaking back, but he speaks to the professor, and the sound waves will travel out, but they'll travel out a little bit more slowly in that direction than in that direction because the water is flowing this way. Let's say there's a point at which the velocity of the water is equal to the velocity of sound in the water. What happens then? The upstream sound waves are traveling as fast as they can, and they don't get anywhere. The downstream ones are, of course, swept over the edge of the waterfall. Assuming that fish cannot swim faster than sound, this poor graduate student suddenly realizes that he's falling over the edge here and yells, "Help!" But of course, what happens to that is that the sound, A, gets base shifted, because each successive crest takes longer and longer and longer to get out. And at a certain point, nothing gets out. So at best, all the professor is going to hear is something like, "Help!" Well, that's exactly what would happen if one had a spaceship with lights, flashing lights or whatever, falling into a black hole. The light would take longer and longer to get out. It would be redshifted. And at a certain point, no more light could get out. So this is actually a good analogy for what a black hole is like. There are some things which are different, but we won't go into those here. Well, I gave this colloquium, and that was that. Except it sort of stuck in my mind, and about 10 years later, by this time I had a position. I was teaching a course in fluid mechanics and at the university, and I was preparing my lectures one day on sound, And I thought about this and I said, well, I should do some calculations. I mean, it's a nice story I told, but what are the, what really happens to sound? And what I discovered was that, in fact, if one looks at these small perturbations of the sound waves, delta rho and delta phi in particular, this is the velocity potential, one finds that the velocity potential obeys exactly the same kind of an equation as a field, a scalar field in this case, would obey around a black hole, for example. There's a metric. In this case, the time component of the upper components of the metric is rho, the background density divided by c squared. The time-space components are the density over c squared times the velocity of the fluid, and the space-space components have that kind of a form. And in particular, if the velocity becomes equal to the velocity of sound, becomes equal to c, those sound waves don't travel to the right anymore. They're dragged off to the left by the flowing water. And if one looks at the place where the determinant of that matrix is equal to 0, that turns out to be a horizon. In exactly the same way as you have a horizon for light around a black hole. So the question is, what happens if I take Hawking's derivation for temperature around a black hole, which took quantum fields? Well, I can quantize these sound waves. They're just phonons. If I took this quantum field and asked how does it behave in this waterfall, and the answer is one can go through Hawking's derivation step by step and get that this system will also have a temperature. The sound waves around this sonic horizon will also come out with a certain temperature due to the initial quantum fluctuations. And if one does the usual fluid mechanics derivation, one gets exactly the same problem as one does in the black hole case. Namely, the sound waves get crowded up against the horizon exponentially, and one has that same exponential problem. But sound waves, we know, can't have a wavelength that's shorter than the distance between the atoms. So one gets an automatic cutoff for these sound waves around the black hole. Well, one finds that the temperature is not given by the inverse mass. It's now given by the derivative of c squared minus v squared, velocity of sound squared, minus the velocity of the fluid squared, divided by the velocity of sound, evaluated at the point where v is equal to c. That's the horizon. So we get a temperature. The temperature is now determined by the geometry of the background fluid flow rather than the mass. As a result, there's no entropy for this thing because the temperature is not a function of the energy that's flowed over the horizon. Well, in 1981, I published this paper where I put an experimental black hole evaporation question mark. And I got a lot of, oh, not a lot, but a little bit of argy-bargy from the editors saying you cannot have question marks in your title. Just not allowed. And I think the reason was what I call Tremaine's law. Scott Tremaine said to me once, whenever you have a paper with a question mark in the title, the answer is always no. Well, this wasn't true in this case. I really didn't know. Might this give you a way of doing an experiment that had relevance for black hole evaporation? The atomic nature of matter prevents ultra-high frequencies. So what does happen? Well, it was Ted Jacobson, again about 10 years later, who came up with a crucial insight, namely that one of the key things that the atomic nature of matter did was to change the dispersion relationship. The relationship between the inverse wavelength and the inverse time, the frequency. Inverse wavelength and the inverse period. For light around a black hole, that's linear. Omega is just proportional to k. For sound waves at low frequencies, it's linear. But if one looks at higher frequencies, it no longer is. So for example, if we look at sound waves in liquid helium, this is some experimental curves for that. You get this so-called roton dip, which they used to think had something to do with rotation and turbulence, but it's just sound waves. In a Bose-Einstein condensate, it starts off as linear and then becomes quadratic. And all kinds of other materials have different dispersion relationships. So we can now change the question a little bit and say, okay, if we have a weird dispersion relationship, does that stop the Hawking process? Obviously, it will change something, but it turns out that as long as the temperature is low enough, it really doesn't change anything. Theoretical calculations show that the temperature is still the same, no matter how you wiggle the dispersion relationship at higher frequencies. You still get the same temperature. So that suggests strongly that this temperature is a very robust phenomenon. It doesn't depend on these e to the 10 to the 5th, even though Hawking's calculation seemed to suggest it did. It's really a low frequency, long wavelength phenomenon, not an ultra short frequency, ultra short wavelength, ultra high frequency phenomenon. But as I said, experiments would be nice. Well, let's try and think of an experiment. Ralph Schutzold, who was a postdoc of mine, came up with the idea, and we did the calculation. And in this case, what one has here is water flowing over some obstacle under the water. And let's assume that this water flow is laminar and irrotational. We get surface waves on the water. It's nice to use something like surface waves because they go at reasonable speeds. I can actually see them move. If I think of a sound wave, it's just far too fast. Sound waves in water are kilometers per second, which I can't see, and it makes it very, very hard to see what's going on. So we've got these surface waves in water, and I can have this water flowing in such a way that in this region it's flowing faster than the velocity the surface waves would have in still water for that depth. And in these regions it's traveling more slowly. This is then a white hole horizon, and this is a black hole horizon. What's a white hole horizon? It's simply the time inverse of a black hole. It's something out of, it's something out of which something can come, but into which nothing can get. And it turns out that the mathematics of this are the same as the mathematics here. And it has a huge advantage. What happens to these waves as they come in, a long wavelength wave, for example, comes in, it gets slowed down as it comes near that horizon, just like a tidal wave gets slowed down as it comes onto the shore for exactly the same reason. The velocity of sound decreases. It comes in here, eventually stops, and then in fact gets swept back out once again. But the thing that gets swept out has a very much shorter wavelength than the thing coming in. And short wavelengths 10, 20, 30, 40, 50 centimeters, are a lot easier to measure than 5, 10, 15, 20 meters. Our lab simply wasn't long enough. So it's far easier to do this experiment than it would be to do the experiment on the black hole. So in 2010, a group of us, Silke Weinferdner, she's another theorist, Ted Tedford had just graduated as a civil engineer, PhD in civil engineering, concerned with fluid flows. Matt Penrice was an undergraduate. Me, who's a theorist. And Greg Lawrence, who was the professor working with Ted on his PhD. A rather motley crew to do an experiment. Not a group you might have picked originally. Here's a diagram of the apparatus. I like this diagram because it looks like something that you could open a textbook by Lord Kelvin or something and see a diagram like this in that book. There's a flume here, water flowing. Pump here pumps the water from the reservoir up into this region. A bunch of screens to try and smooth out any turbulence coming in here. The water flows over this obstacle, sort of wing-shaped obstacle. It has to flow faster over the top than down on the sides. A little screen here which we could dip into and out of the water, which produces water waves that travel upstream. And then there's a gate here which allows the water to fall over into the reservoir. So that's the experiment. We have water flowing. We jiggle this up and down via this motor. We jiggle this up and down, send waves at the white hole horizon, and measure what comes out. How do you measure what comes out? Well, I mean, this was one of the things that I really scratched my head about. But it turned out that Ted Tedford came to our rescue because he developed this technique in his PhD for measuring interfaces. You fill up the water with rhodamine dye. It's a fluorescent dye. The mean free path of the green laser light in that rhodamine dye is of the order of less than a millimeter. So one very accurately, by looking at the fluorescence, can see where the surface of the water is. And one can measure it to much better than 1/10 of a millimeter. And this obviously doesn't disturb the flow of the water. One of my previous ideas would be to stick little wires in and use resistance or capacitance, but of course those little wires are going to affect the flow and is not the best way of measuring. Then one comes from the side and takes a picture of this to see exactly where that surface is. Another advantage, this is laser light which has been spread out into a sheet via a lens up here, a cylindrical lens up here. As we know, laser light has speckle. Speckle is not good for measuring heights. But the fluorescence that's emitted by the water is completely incoherent. So it doesn't have speckle. And one can much more accurately measure where that surface is. So just to give the result, these are some of the examples of waves coming in. The central peaks here are the waves that come in. We can't measure them accurately. Some of those have got wavelengths of 60 meters, and figuring out what the wave is like on 60 meters when all you can see is the first half meter of the wave is really difficult. Theoretically possible, experimentally difficult. But these are the waves that are coming out, which have wavelengths of the order of 20 centimeters, 40 centimeters, things like that. And in particular, what turns out to be important is the energy in these peaks here divided by the energy in these peaks here. That gives you the number of particles, if you were doing quantum mechanics, that gives you the number of particles that would be created by the quantum system. These are effectively the so-called Bogoliubov transformation coefficients for those of you that know your quantum optics. And this squared divided by this squared is the number of particles that are emitted in the quantum system. And when we plot that, this was what we got. Now, if the emission, the quantum emission, would be thermal, it would be a straight line. The x's are what we got. Notice that this is the logarithm, so we're going over 5, factor of 10 to the 5th in the intensity of those waves, and over a factor of something like 10 in frequency. Well, to me, that's those x's are a straight line. This is our best fit, so there is some error, but it's a lot less than one might have thought. Incidentally, where is it? This red line here is where we made the measurement just off frequency. One frequency bin off of the frequency that we sent the waves in. Notice that the difference between this and one of these curves gives one a feeling for the noise that one has in the system. So, what we find is that this system really does or really would have a thermal spectrum if one could see the quantum phonons being emitted by this white hole horizon. The frequencies are about 1/8 of a hertz, and those of you that are facile with them know that 1/8 of a hertz corresponds to a temperature of about 10 to the minus 12 Kelvin. So the chances of us being able to measure that temperature of quantum emission, at least in Vancouver, our water is a little bit warmer than that. A little bit warmer than 10 to the minus 12 Kelvin. But what this tells us is that if we were able to measure the quantum emission, one would get a temperature, or one would get a thermal spectrum for the radiation. The predicted one, it's very hard to figure out exactly where the horizon is, but our best estimate is that the temperature that one would expect by looking at the behavior near the horizon is somewhere between here. So this is at least consistent with, this result is at least consistent with that. Now, as I said, this isn't quantum, but Einstein came to the rescue because in 1919, he argued that if you have a system and you look at the stimulated emission from that system, and what we're doing here is stimulated emission. We send in a wave and we measure the amplitude of the waves that come out. This is a stimulated emission system. If one measures the stimulated emission from a system, one also knows what the spontaneous emission is. The spontaneous emission is directly related to the stimulated emission. He didn't put it in those phrases, but it's basically exactly given by those Bogoliubov coefficients that I plotted before. So in that sense, one could say that this is definitely a measurement of the thermal spectrum. Of course, you might distrust Einstein, or, come on, water, quantum, got nothing to do with each other, right? So it would be nice to be able to see the quantum noise, the quantum spontaneous emission directly. Is it possible to do that? Well, as we notice, we need things like temperatures of 10 to the minus 12 Kelvin. That's a little hard to find. However, we have things that do have temperatures of that order. Bose-Einstein condensates. They have temperatures of around 10 to the minus 11, 10 to the minus maybe even 12 Kelvin. Perhaps one could use them. If one looks at the Gross-Piatevsky equation, one finds that one can write it exactly in the fluid form and get exactly the same predictions for the Bose-Einstein condensate as one does for the water, sound waves and water. One gets an extra term in here, which is sometimes called the quantum pressure, and all that does is to change the dispersion relationship in the Bose-Einstein condensate from being the linear one that you expect for sound waves to being a quadratic dispersion relationship. And that's the role that this term plays. So it's important only at high frequencies. The quantum pressure also tends to smooth out flows over a waterfall so that even if you push the fluid with a square wave, the waterfall is smooth, which is also good. Steinhauer, about 3 years ago now, in Israel, at the Technion in Haifa, decided to do this experiment. So what he had was a long Bose-Einstein condensate, about 100 micrometers long, and he used a laser field here, an attractive detuned from the resonant frequency of his Bose-Einstein condensate in such a way that it would attract the potential of the atoms in this region would be less than there. So the atoms, as you shine this laser beam in, these atoms will basically fall over a waterfall, and you'll get this little waterfall here, which you could make into a black hole by sweeping the laser field with some velocity v, which is larger than the velocity of sound. Velocity of sound in Bose-Einstein condensates is about 2 millimeters per second, so it's not too hard to sweep. Sweep it over there, and if one had this being larger than 2 millimeters per second, you get a black hole being formed just at the edge of this laser field. We have a sharp jump in the potential. The quantum pressure would smooth that out. So this waterfall creates a horizon. Downstream sound can travel into the horizon. From upstream, it can't get, it can't get out. So let me go back. So this way, sound waves in this region, oops, my laser pointer is dead. Sound waves, and so is my cursor. Oh well. Sound waves can't get out from this direction. So this acts just like a black hole. And one can now do an interference type experiment. This isn't exactly what he did, but one can imagine shining light through the Bose-Einstein condensate. The Bose-Einstein condensate is sticking in and out of the screen. And then interfere that with light, this other light, in order to get an interference pattern, or get a pattern here, which tells you how much slower the light has traveled through that parts of the Bose-Einstein condensate than it does through other parts. So one can measure the density, the integrated density in the Bose-Einstein condensate in this way, and figure out what the fluctuations are in that. Those fluctuations are like measuring the momentum of a quantum field. So here are some of his diagrams from an earlier paper. Here's the edge of that laser field, which is sweeping down with a velocity. Here is the density of the Bose-Einstein condensate. And this sitting right here is the edge of the black hole. This is what the Bose-Einstein condensate looks like without the laser field in there. So the fluid here is moving, the fluid here is stationary, here the fluid is moving away that way, and the laser beam is moving upstream in this direction. The important thing that he did was to look at the correlations in these density fluctuations. And in particular, he discovered that there was this anti-correlation. X equals 0 is the horizon. X primed equals 0 is the horizon. So this is density at point X versus density at point X primed, done by taking 4,000 different realizations of the system. And you see these anti-correlation lines, little whiskers, going off in these two directions. Those represent the creation of density fluctuations of particles by this horizon of this analog of a black hole. This is, if you do a cross-section of this density correlation function in this direction, you get a curve that looks like this. It's very noisy. He argues that this is thermal. I don't think you can really argue that. It's not inconsistent with thermal, but it's too noisy to really say that. One of the problems that, I don't have that here. One of the problems you have is if you look at the correlation function and you ask what is a measure of the entanglement, quantum entanglement between the radiation going off in the two edges, you get a curve that looks something like this. In his original paper, it disappears down around here. He's just published another paper in which that entanglement measure is actually goes down to much lower frequencies over here. So I think he has made a reasonable case that what he sees is particles being emitted by this horizon. They're anti-correlated with each other, but they're anti-correlated in just exactly the way that you would expect if those density fluctuations were entangled with each other on the two sides. Entanglement is a quantum property. So this is quantum radiation, which at least looks approximately thermal and certainly looks quantum. So one can argue that this is the first detection of a fully quantum emission by the particles at one of these analog horizons. So if one believes in the analogy with black holes, this, I believe, gives support to Hawking's calculation. Notice that this system is very different from the black hole, a very different dispersion relationship at high frequencies, a very different medium. Despite that, you seem to get this thermal spectrum being given off by this system. If one combines the water experiment and this Bose-Einstein condensate experiment, whether that's valid, leave up to you. The water experiment shows that the spectrum is thermal, but says nothing about the quantum nature. This says that you get quantum entanglement, but the thermal nature is far too uncertain to make any real claims about that. But putting them both together, I think one has a reasonable argument that this system really does have thermal quantum noise. This horizon has thermal quantum noise being given off. Various other suggestions have been made. What am I trying to say here? Yeah, either of these alone is not sufficient. Let me not spend time on this. So I hope I've given you a feeling that analog systems are a rich arena in which we can carry out experiments which can cast light onto the quantum nature of things like black holes. I mean, in many ways, it's amazing that, well, somebody said to me after I gave a talk like this, do you mean that in 20 years we could have our undergraduate students doing an experiment in their undergraduate lab which supported black hole temperature, like that water experiment that we had there? And the answer is yes. There are many other systems which people have looked at. One can, for example, shine intense laser light into diamonds and change the refractive index in such a way that you get a white hole black hole pair there, and look for quantum emission from that white hole black hole pair. This was first suggested by, well, it was actually first suggested by Ralph Schutzhold and myself, but then Daniel Faccio implemented it in silica glass. He argued that he saw something. The problem was the figures didn't really add up. But it's a very promising area, and he now wants to try and do this in diamond. He was at Heriot-Watt University. He just recently moved to Glasgow. There's a group, Koenig's group at St. Andrews, who's also trying to do similar experiments. This also raises philosophical questions. In how far should we trust these analogies? And in fact, there have been a few philosophers that have written papers on this recently, arguing that yes, one can actually use analogies to learn something about the system that they're analogous to. For me, a minimal answer at least is that the robustness of this phenomenon, namely that it occurs in a whole bunch of different situations, gives one much more faith that it's also going to be true in the black hole situation. That's the end.
Thank you. Questions?
Yes.
So, do you know of any other situations where this approach of using analog systems is being used to find things that are very difficult to observe normally?
To understand normally. So, I mean, another area in the gravity case is, you know, in inflationary cosmologies, the density perturbations that eventually form our galaxies, our stars, etc., all come from this similar kind of quantum amplification process in the very early universe. The space-time is rapidly growing in size. Distances between objects are changing. That change, that time dependence in the propagation of fields also creates particles, pairs of particles. And people have, for example, suggested taking Bose-Einstein condensates and changing the velocity of sound by adjusting the interaction strength between atoms, which one can do with, you know, things called Feshbach resonances, you know, changing the spin energies. One can actually tune the velocity of sound so that that velocity of sound can change, making it look to these waves as though this whole Bose-Einstein condensate was expanding in an exponential fashion. Doing that, one can see, again, density fluctuations grow which would be then an analog to the density fluctuations which we would have in our universe in an inflationary scenario. Again, that's it's very difficult to carry out the original experiment because we don't have too many other universes that we can look at. And this is also, there are also other fields of physics where sort of condensed matter analogs are starting to be used in order to try and understand much more difficult physics in another area. Right now, I can't dredge one up, but.
Well, thanks.
So I guess before 2000, I've been looking up some things about protons, and it seems everyone has a different explanation for what these things are. And you said that that little roton curve can just be explained by sound waves.
Yeah.
What do you mean by that?
Well, it's just a change in the dispersion relationship of the sound waves. If you take, in your condensed matter course, you all got this little balls on springs, right? If you, for example, now have not only nearest neighbor interactions, but also put next to nearest neighbor interactions, you can get dispersion relationships that look very similar to those. Again,
Any funny roton model?
there's no, this is just harmonic oscillators with little, and these are just the longitudinal oscillations of these little ball bearings or whatever it is that you're using. And they give this dipping kind of dispersion relationship for the sound waves traveling along this string. So that's an example where, just ordinary sound waves can explain that with the appropriate interaction between the atoms can explain that kind of a curve. Yes? Oh, sorry. Sure.
So, following up on what you said in the end, would there be, how would an analogy like this with the mechanical system fail? What aspects of the original problem would you not see from something like this, or something that you might not expect to see or that you might miss?
Well, one of the ways, I'm not sure this is answering your question, but one of the ways that you could use a system like this to probe areas in, let's say, the black hole case, which you just couldn't any other way. And in the black hole case, one expects that once one gets up to the Planck frequency, this is the frequency, for example, where, if you have a piece of energy, a photon, and the energy of that photon, the amount of, for a single quantum excitation, the energy in one wavelength would give you a black hole of the sort of wavelength. This is the very hand-waving thing that Planck came up with in 1900 already, once he introduced H. Anyway, above the Planck scale, we've got quantum gravity. Nobody has a theory of quantum gravity, so we don't know what's going on. If one looks, for example, in that curve, the dispersion relationship for liquid helium, as one gets to wavelengths that are shorter than the distance between the atoms in the liquid helium, the dispersion relationship just all goes to hell. There is no dispersion relationship anymore. It's just a mess. Again, it's really hard for us to know how to model anything going on in that regime where you have, fewer than one atom in a wavelength, for example. So one could imagine doing an experiment in liquid helium in which the radiation that was produced at the end originally came from that region in the dispersion relationship, which you don't understand. Or in Bose-Einstein condensates. You know that once the wavelength gets less than the spacing between the atoms, you no longer trust anything about the system, your understanding of the system. And there you could imagine having the radiation that comes out at the end coming from that region where you don't understand anything. If you still saw thermal radiation, you'd really have strong evidence that, Planck scale, Schmonck scale, who cares? It doesn't do anything. You know, it's unimportant because it's unimportant in the analog system. That's of course not a proof, but I think it gives one a lot of faith that that's the right answer.
I have a question regarding this equivalence between the Hawking radiation and this. So I have a question regarding the equivalence of the Hawking radiation and then the radiation you just see by being an accelerated observer. So for those of us who don't know anything about gravity, we're given this kind of simplified picture of Hawking radiation, where near the event horizon, I get this particle-antiparticle pair. One of them zooms in, and the other zooms out, and that's the radiation.
Right.
Is there a similar sort of oversimplified picture for this this radiation you see by being accelerated?
The problem with Hawking's, that explanation that you gave, that hand-waving explanation, was one that Hawking produced for a Scientific American article about a year after he published his paper. The problem with it, it has no calculation that supports it. It was simply a, you know, a nice picture. But, you know, you would like pictures like that to say, okay, here's this calculation, which shows that's the kind of thing that's happening here. There is some evidence that perhaps it's right. For example, if one looks, one can calculate the energy momentum tensor of this quantum radiation. One has to, it's infinite, so one has to do regularization and so forth. And if you do it such that for flat Minkowski space, everything is zero, the energy is all zero, which you would sort of think is the right answer. You do that near a black hole, and what you discover is that the radiation from a black hole, you get radiation heading out to infinity, which carries positive energy out to infinity, which is what you would expect. There are all these particles being given off, they're carrying out energy. That doesn't come from the horizon. It comes from a region of around 3m, 1.5 times the radius of the Schwarzschild radius. Inside that, you also get radiation going into the black hole, but of negative energy. It, of course, has to be negative energy because you want energy conservation. The positive energy going into infinity has to come from the black hole. So somehow you have to decrease the mass of the black hole. The way it decreases is because this negative energy is going in. So that makes it look like there's something going on outside the horizon at around 3m, let us say, where this energy is being created in this sort of pair kind of, which reminds one a lot of Hawking's sort of diagram, that you have something here which gets out and something here which goes in. It's not the horizon, it's well outside the horizon. So there is some support for his picture. And you know, there's more truth in it than one might at first think, looking at the previous calculations that have been carried out. But it's still somewhat, 40 years later, is still a somewhat confusing field. Yes?
Is there any answer to the black hole information paradox in these analog systems?
So that's, the information paradox is, the story goes something like this. Let's say that we make a black hole from laser beams or something, which are in a pure state, a pure quantum state. They form a black hole. The black hole starts to radiate. What's given off looks very much like thermal radiation. If it's thermal radiation, then it's incoherent and carries entropy. So if we wait long enough for the black hole to radiate, you've got all this thermal junk out here whose temperature gradually increases as you go into the future. No black hole. So you start off with a pure state and you end up with this density matrix, a mixed state, highly mixed state, no correlations. How in the world can you turn pure to mixed state? This violates unitarity, the claim is. All kinds of nasty things, the world will come to an end, we'll all be thrown out of jobs, we will all have to do ditch digging for the rest of our, there are all kinds of doomsday scenarios attached to this. And that's called the information paradox. There are a number of ways, however, out of it. Remember that you've got that region inside the black hole. And that region inside the black hole is, in fact, space-like separated, in relativistic terms, from anything outside. And it stays space-like separated even after the black hole disappears. So if stuff goes inside that horizon, it's gone. So information can go in. If you believe in the classical picture, it falls off the edge of the universe at the center, but it doesn't have to do that. It could just stay in a separate universe, for example, a baby universe, blah, blah, blah. So this is sort of the information paradox, but it's tightly tied to this notion of entropy. The problem, as I said, is that these dumb holes don't have entropy. That relationship between the temperature and the energy that you had in the black hole, that the temperature was 1 over the energy, just doesn't exist for these analogs. So the equivalent of this information paradox simply doesn't exist there. So unfortunately, one can't use it to answer, use that analogy to answer the question.
Okay, thank you very much, and there's a
Thank you.
reflection following, so if you have further questions, you can ask. Okay.